Broadcast is now starting. All attendees are in listen-only mode.
Good evening and welcome to our webinar on nightmares of a container orchestration system. Even though it's already 8 p.m. over here, we'll still wait for 2 more minutes or so till more people show up, because so far only a fraction of the registered people have signed in. Until then, let me just give you a brief intro of what you can expect for tonight. So there are a lot of talks which tell you what are like the best practices of your clusters, or show you fancy demos, how cool it is to run their container orchestration system. But often what I personally miss are the stories, what easily breaks the system. And having worked with both Kubernetes and DCOS, I can tell you for both systems a myriad of ways how to break them. And so here are just some of the experience which you should, of things or approaches you should use when you want to break your cluster, or what you should avoid when try to have a production container orchestration system up and running. So I hope this will be useful for many of us. Some of the examples and screenshots will be focused on DCOS, but most of it you can just apply to any container orchestration system. So I hope you enjoy it. As mentioned, we'll start in a few minutes. 2 more minutes. All right, it's 8:05, so I guess it's time to start. Welcome again to our webinar on nightmares of a container orchestration system. So tonight you'll learn what you should or shouldn't do to your container orchestration system. As mentioned earlier, some of the examples might seem DCOS, Mesos, or Marathon specific, especially the screenshots, but most of them apply to really any container orchestration system out there. Me, that's Jorg. I'm a technical lead for community projects at Mesosphere, meaning I deal with a lot of projects using containers and a lot of people running things in containers. And virtually joining us, so he won't be here for real or even joining the webinar, but thinking of us probably is Jan. So Jan used to be a support engineer at Mesosphere, and now he's a solution architect. And he is kind of the person who experienced many of those cluster fails. So he was the person who was called at 3 a.m. at night when a cluster was breaking. And so Jan's intention was, or Jan's biggest wish was, that people would follow some of these advices and avoid some of these nightmares we'll see tonight. So the scope of Jan's nightmares, as mentioned, I'm working at Mesosphere, and we have an open source project called DCOS, short for Data Center Operating System. And that's basically a distribution of Apache Mesos, which allows you to both run containers as well as like big data frameworks such as Spark, Flink, Kafka, Cassandra, easily on any kind of infrastructure. So it's both a container orchestration and a big data framework orchestrator or scheduler, if you want, in that way. And as mentioned, this is where both Jan and myself, we got into contact with all those containers and all the nightmares you'll see on the following slides. I guess the first nightmare to be avoided if we're talking about container orchestration systems is having none at all. So we still see a number of customers which actually deploy and manage all their containers by hand. So just to give one example, there used to be a customer who then switched over to a container orchestration system. They had a big spreadsheet, and then every Friday afternoon they would meet and check whether the number of containers they expected to be running in their infrastructure would still be running. So for example, that spreadsheet would say we expect that 100 containers of our web servers are running. On Friday, they would check that only 95 were running because 5 of them had failed during the last week. So they would restart 5, and their spreadsheet would be telling the truth again that there are 100 containers up and running. And as you can see, this is probably not the best approach because first of all, it requires an operator to step in and actually restart those containers. And secondly, it's a lot of overhead, and for a long time, for almost, it could have been the entire week, there were 5 containers less running than expected. So this seems to be a perfect job we actually want to throw over to a system to take care of. So if we look at a container infrastructure without orchestration, we have a container runtime that could be Docker, this could be Rocket, this can be Cryo, or UCR. So it doesn't have to be Docker, it can be any technology who can run a container or isolate a container. And then we have our applications on top. And this would be exactly the scenario which I like to refer to as spreadsheet scheduling, where you have either some self-written script or something, some spreadsheet and some operator who actually has to check that. Note that even if you have written some scripts for that, this is a really hard problem to manage all edge cases. And probably in 90% of the cases, your scripts will work fine. But then there are those 10% or less of edge cases where you actually will have failures in your infrastructure, which is then pretty hard to debug. So container orchestration is also, it has more aspects than simply restarting failed containers. So the first part, the actual scheduling part, is about where to place nodes, about restarting failed tasks, about upgrading. So imagine you want to upgrade a container from web server version 1 to web server version 2, and you want to do that in a fashion that the users don't even notice that. And this is also where a container scheduler can be really helpful in gradually changing over those instances to the new version. Scaling is a vital task for a container orchestrator. So if you want to scale from 5 instances to 10, there should be an easy way that your container orchestration supports that. As a warning ahead of the other nightmares, especially if you have state, scaling down can be a challenge. So always when you scale down, meaning you kill containers, you should be worried about both what is the persistence attached to that cluster, and secondly, what are other things which might be affected. So imagine a web server with long-running sessions, or a typical example for long-running sessions could be a MySQL server, where a lot of users are attached. If you now kill that containers, all their connections will drop. So typically, you also want to implement some kind of connection draining. The next important thing a container orchestrator takes care of is resource management. So which user or which container is allowed to use how much memory, how much CPU, potentially even GPUs, or persistent disk space. And also manage that in a way that it gets scheduled to nodes and not one load gets overloaded with all CPU bounded apps, for example. The last, but in my opinion, most important part is service management. And service management is about how can I use individual containers and connect them into like a meaningful service. Typically, if we have a service, it's not a single container running. Either it's a number of instances of a container running, as the example with the web service we saw earlier on. Typically, a single web server won't really help you. But if you have multiple of them, this can already be value for you or the use case you're working on. More often, it is that you actually have to take multiple different containers and attach them to a larger service. So there might be a database backend, there might be a web server, there might be a server containing some business logic, for example, written in Java. And now you need to connect all those individual servers into one running service, which is actually doing useful things. So with that, our architecture diagram from earlier looks like that. Kind of across all the nodes, across all those container runtimes, we have our container orchestrator taking care of service management, scheduling, and resource management. So once we have introduced that, what are next nightmares? So one really important thing is to still keep backups, and backups especially first for the state of your container orchestrator. So for example, which instances are running in which configuration. And we'll see that throughout this presentation, this is a really important theme, that you should always be able to redeploy your entire infrastructure from code without much effort. So actually your entire cluster, including the state, should be backed up. And state also refers to stateful services. So for example, if you have a Cassandra database, a distributed database running in your cluster, you also want to back up its state. Next, equally important thing is monitoring. So it's not sufficient to simply check the cluster state every morning, but you should have automatic monitoring, and then also automatic triggers if something goes wrong in your cluster. So for example, it's a typical problem, especially when using Java, out-of-memory exceptions, because you have sized your container too low. On the other hand, it's also not good if you size it too big, because then you're wasting resources. So what you want to be able to detect is an out-of-memory error, hopefully before it even occurs. With containers, the annoying thing about out-of-memory errors is that once I use more memory than my container is allowed to use, it will simply be killed by the C group's out-of-memory killer. So my container will simply be gone. So it's a real problem we typically want to avoid. Also, metrics I want on different levels. I want to know whether my cluster overall is healthy. I want to know whether individual containers are in a healthy state. And then also the resulting services should be working. So something to monitor for example, latencies. And another advice for monitoring latencies, it's typically, often people start by monitoring something like average latency or so. I would instead monitor percentiles, so that you know what is your 95 percentile of tasks, or even 98, 99, and so on. This gives you a more meaningful insights than just average latencies or any average metric. Networking. So the picture on the left, it's probably hard to see, but that is the entire point of it. It shows the shift in networking. So about 10, 15 years ago, the networking bottleneck for a data center typically was the outside connection. So there was, most data traffic was coming in from the outside. Nowadays, especially with containers and microservices, this has changed, and we have a lot more in-cluster traffic compared to outside cluster traffic. And this also brings challenges to networking in general. So when considering how to set up your system, you should consider the following networking challenges up front before setting up the system. How can I achieve connectivity so that actually task A can talk to task B in some way? It needs an IP address, and they have to be able to talk to each other, and so on. Secondly, and this is a typical pattern if you spin up any microservice-based system, is load balancing. So as you have not a single web server, but you have millions, or not millions, but you have multiple instances of that, you usually have between different services in your microservice architecture, you have load balancers, which will actually then distribute the load to different backends, so to different API servers, to different web servers. And even choosing those load balancers is a important task. So for example, you have the choice at which layer it should operate. Do I need something as HTTP session control? So do I need a layer 7 load balancer, which is pretty high up in the networking stack? It gives me a lot of features. So for example, I can support authentication. I can pin an entire user session to a particular backend, so make sure that all requests from one user are ending up at one backend. Or am I happy with a layer 4 load balancer? So lower in the networking stack, which basically just can round robin all packages which is get to different backends. This is sufficient for many microservice architectures, and it gives me much more throughput compared to a layer 7 load balancer because it has less work to do. Next thing is, as we're talking about large clusters, and if I deploy a container on a cluster, I don't want to have to pin it to a particular node. We have to be able to figure out where things are running. So my web server has to be able to figure out where the database backend is running in the cluster without knowing its location up front. So a typical pattern for service discovery is to introduce DNS names or DNS-like names, which can be resolved from anywhere within the cluster. And then also isolation, connecting back to connectivity, that I have to be able to separate single parts of my cluster. Imagine you have a multi-tenant cluster and you don't want that task A from a particular user are able to talk to task A from another user because you want them on separate isolated networks. Container images themselves. So if this is a sample app definition, so this is for Marathon, but it looks very similar if you specify a YAML file for Kubernetes deployment. And the thing here is that we just specified an image called Ubuntu. What is the implication of that? If we just specify an image named Ubuntu, this means that implicitly Ubuntu latest will be pulled. So that would be Ubuntu : latest if you want to spell that out. And now imagine you have using this Ubuntu image to run web servers again. And again, we have 100 web servers running. Now, the next Ubuntu release comes around, and Ubuntu latest is all of a sudden pointing to 17.4, whereas your 100 instances before are all 16.04 Ubuntu version. And now one of them is failing and restarted automatically by the container orchestrator, but all of a sudden you have 99 Ubuntu images with 16.04 and one with 17.04 running in your infrastructure. And believe me, this mix of different versions makes debugging really, really hard. So you should always have a tagged container image. So for example, Ubuntu : 16.04 as one example. And you personally, if you're developing your own or pushing your own Docker images, in theory, you can overwrite them. And unfortunately, Ubuntu even is doing that with some releases. But if you push a tag into your infrastructure, you should keep that tag as immutable. So whenever you have pushed an image once, you shouldn't push to the same tag again. So if you integrate it, for example, with the CI/CD pipeline, typically you could include something like the build ID or something unique into the container tag, into the container image tag you're pushing into your registry. And registries is the next topic. So I've seen even some production clusters which are using Docker Hub to pull all their images. This is very easy. You don't have to set up a registry, but first of all, you're in no control which images are being pushed to Docker Hub. So Ubuntu can override it with its own new latest image. Whereas if you use your own private container registry, hopefully inside your cluster, first of all, you're in more control which images end up in that registry. And secondly, you're also in control you also have much lower network latencies because it's running inside your own cluster. So it's highly recommended to spin up your own container registry, typically backed by some distributed storage. So if that registry fails, it can easily restart on any node in the cluster. But you shouldn't solely rely on Docker Hub. Also, if Docker Hub has an outage, which sometimes has happened, you can have large impact into your infrastructure, which you can't fix yourself because it's out of the scope of your control. While when it's in your own cluster, you can control it yourself. Repeatable Docker builds. So Docker has this nice feature. I can just go into a container, I can play with that, I can install all images, and then I could do a Docker commit. You should always be able to rebuild your entire infrastructure, as mentioned earlier, and that includes the Docker images. And so all Docker images running on your container orchestrators, they should come from Docker files, which you have versioned, and you can repeatedly build from them. Also, it's good practice to keep the images minimal, and therefore Docker has two cool features. One is called multi-stage build. So imagine you have a container which first needs to compile a certain framework and then goes on and just using the binary on. Then you can use a multi-stage build, whereas the first stage has all the build environment, the compiler, and everything else you need, and the final image simply has the binary you just generated. Also, to keep sizes small, if you have a standalone binary, as for example a Go program, you can easily build from scratch. So from scratch means that there is no file system layer, as for example Ubuntu 16.04 underneath, but simply a blank file system image. And that really also makes the sizes of those images much smaller. So from scratch, if your Go binary has 1 or 2 megabytes, this will be the size of your container image, whereas if you use Ubuntu as underlying image, your container image will have somewhere around 120, 130 megabytes minimum. And that adds up to a lot of network traffic, either external if you're pulling from Docker Hub, or even internal if you're pulling from your private registry. UI. So most of those container orchestrators, they have UIs where you could actually deploy something as well. As again, you shouldn't use that. I sometimes use it for demos because it's nice. For any production cluster, I would actually urge people to disable the UI. So all deployments should be done via API endpoints, and all deployments should be done hopefully from a CI/CD system, so that I, as a developer, I can't really even push app definitions into the production system. I always have to go via a CI/CD platform where I would push my app definition into a version control system. Then there can be some sanity checks, some test running, and then it's automatically being pushed into the production environment. So this is kind of the best practice of closing off your cluster from as much manual interaction as you can and only have automated deploys, because it makes, first of all, deployment easier. You have more control of what's running there, and also failover cases are easily handled because you can simply restart your entire cluster from the infrastructure definition you have. Disk usage. Disk usage is one of those things you should also monitor for. So especially Docker and logs, they are great in filling up disk space. So Docker, when it's fetching images, or when it's even starting containers, it will keep them around for a while. So cleanup of Docker instances and images is kind of a must. Docker has this --rm tag, which will automatically delete the container instance. And you can also use Docker prune. I personally there's a GitHub Spotify project, Docker garbage collection, which will automatically clean up your cluster once it's running there. And this is, for example, similar to what we use on DCOS. And again, monitoring the available disk space is the vital key here, so you get alerted before something goes wrong. Resource constraints. So resource constraints are one of those hard things to pick. So they basically tell how much maximal resources are available for your server. And here, if I'm starting an app server with half a CPU, 32 megabytes of RAM, and this is running in a Docker container, this is probably too little, because Docker alone probably will use more memory than that, especially if it's using an Ubuntu image. Keep in mind that those memory constraints are hard limits, and don't set it too low either. So if you're setting it too low, for example, with Java, it should be higher than the maximum heap space, because Java has some overhead over the actual just heap space it might use. So adding some overhead, like I would say either factor 1.5 to factor 2 of the heap space if you're running Java-based application, it's a good rule of thumb. But again, the easiest thing is to monitor that and get a feeling for how much memory does your container, your program, your app actually use. Zookeeper cluster size, and in this can also refer to etcd. So basically, any quorum-based system which needs to be able to make a decision. So it should always have an odd size. So 3, 5, or 7 are the most common deployments. Because they have to have a majority decisions. And if I have 4 nodes, I actually need 3 of them to make a majority decision. And so I end up with pretty bad fault tolerance, because as soon as 2 nodes are failing, my entire system is down. And keep in mind, so this is also the case with 3. As if I have 3 nodes, as soon as 2 of them are down, also my quorum will be unavailable. But if I only have 3 nodes, the chances of 2 of them failing is less than if I have 4 nodes and 2 of them are failing. My personal recommendation would be for those quorum-based systems of having the number of 5, because with 5 you can survive 2 failures in your cluster. And there's one point in your lifetime where you actually introduce an artificial failure, and this is during upgrading. So if you're upgrading your Zookeeper, your etcd cluster, you'll take always 1 node off, upgrade it, and then have it rejoin the cluster. But during that time, there's already 1 node missing in the cluster. And if you have a quorum size of 3, during that time, you couldn't survive an additional node failure. Health checks. All container orchestration systems give you some way of specifying health checks. And this makes it very convenient for the container orchestrator to understand whether your application is healthy or not. So you have multiple options when you're running on DCOS. So you can choose Mesos or Marathon-based health checks, command, or HTTP. But the most important lesson is just specify them, because it impacts a lot of components. So for example, also load balancers in the system, they'll only consider healthy backends. And if your app is not healthy, if there are some failures, it will actually not be considered for load balancing backend. NoSQL Datastores. As we're talking about clusters, often you also need some kind of solution for storing data. And I see a lot of people moving to those NoSQL Datastores, which is also great. Just you have to understand what it means to move to them. So for example, I've seen people replacing a Postgres instance with a Cassandra cluster. And how did they do that? They exported all their data, all their models, all their queries from Postgres, had to modify them a little tiny bit to fit to SQL, but they used the same data models and the same queries on Cassandra than they did on Postgres. And this typically will end up pretty badly. First of all, they were running into issues because Cassandra had different guarantees in terms of what it means. So it's the asset versus base consistency guarantees. So they were getting stale results after they had written their data, simply because they didn't understand that Cassandra is an eventually consistent system, whereas Postgres is immediately consistent due to the asset constraints. Secondly, they were getting really bad performance because the underlying way in which Cassandra stores the data physically is way different from Postgres, from all relational databases. Even though it seems through CQL and how it's being marketed as a relational database, underneath it's not. And so you have to be careful of that when modeling your data and also modeling your queries accordingly. Removing frameworks, especially the ones which have state. So if you run something which has requested some state, so both in Kubernetes or Mesos, you have to be careful how cleanup is being done. There are ways, both in DCS and Kubernetes, that this will be cleaned up automatically. But overall, you should follow uninstall instructions rather step by step and make sure that you really remove all state in the cluster. Otherwise, it can lead to very annoying debugging sessions later on. Also, what I still see from time to time is this misunderstanding of what containers really are. So there are people who just replace all the VM instances by containers. And I'm not saying that this is a bad strategy in general. I think in many cases it makes sense, but you should be aware that there are different isolation semantics. So a container, those are basically process groups running on the same kernel, whereas with virtual machines, you get a kernel per virtual machine. So they are way more isolated than containers. On the other hand, of course, you have a lot of performance overhead when running virtual machines compared to containers. So there are trade-offs being involved. And yeah, as mentioned, containers, what are they actually? So first of all, containers, they are just isolated process groups. So they are process groups running on the kernel. If you're using ps-aux, the Linux command, you see all processes running on the kernel. From the host, you'll see all processes running there. But they're kind of constrained in what those process groups can see and how much resources those process groups can consume. And this is done by two kernel features called namespaces and C groups. Also, when talking about containers, we should make sure which part we're talking about. Are we talking about a container runtime? This can be Rocket, this can be Docker, or something else. So this is the system which actually spins up those processes and creates the C groups and namespaces for them. Then we have the notion of container images. So container images, they're this Ubuntu latest or Ubuntu 16.4. So they're kind of a template, a file system template I can use to start up Ubuntu 16.04 container. And once I've started that up, I have a running container instance. So for example, I can also have multiple instances of Ubuntu 16.4 containers running on my laptop here. So those are kind of the system things or concepts we should distinguish when we say simply container. One thing as also the concept of container images, we not necessarily need a container image when spinning up containers. So here's a sample app definition for a Java application. And this is Java application. The only dependencies is the jar file with the application itself and a JRE. So what this app definition is doing is kind of creating the container image on the fly by simply downloading first the application jar and then the JRE jar. And this is then the running container. So we don't need this Ubuntu 16.4 image to spin up a container. When using containers, especially for Java, you should be aware that not all technologies are aware of those C groups and namespaces. So if you want it in simple terms, not all technologies are aware of containers. And Java, previous to version 9, is one of them. So when Java starts up with the default settings, it will look at the number. It will look at the number of cores available on the machine where it starts. And imagine you have developed your Java application on your local laptop where you have 2 cores available, and now you're moving to this big production system with 48 cores. You being a responsible developer, you have packaged your Java application in a container, and this container should have 2 CPUs available. So at maximum, Java can use those 2 CPUs you assign to it. But as you're starting on this 48 core machine, Java will see, oh, I have 48 cores available, so I'll use 48 threads for garbage collection. My default fork pool size will be 48, and so on and so on. So what will end up happening is your Java program is just switching between different threads and not doing any actual work. So when running Java in containers previous to version 9, you should be careful in which way you set those default values. So you should override a number of default values in that case. And here we just see why this is failing. So the JVM running, it will access the host system. So it's not aware of any C groups isolation. And if we're using traditional VMs, this works because it will access the kernel of the guest operating system running there, and that will only have 2 cores available. Whereas with containers, it's only the C groups isolation layer which will simulate that there are only 2 containers available to the cluster, but the host operating system will still say, hey, I have 48 cores available. And this is then exactly the scenario. We try to deploy 10 JVM containers onto a 32 core box. So we have 10 times 32 cores seen by each JRE. So we start a total of 320 threads for the fork join pool, 320 threads for garbage collection, and so on and so on. So you can imagine this is not great for performance. Mesos modules. So this is something Mesos specific, but overall it says that you should be careful when replacing default components. So both Mesos as well as Kubernetes, they're very modular. So you can actually replace individual components such as the API server, such as the scheduler. But you should be aware that this often has more consequences. So the default modules, they're heavily tested in that setup with all the other components. And you should be careful that if you replace something, it will make debugging much, much harder. So stick to the defaults unless you have a very good reason to change the default components. Linux distributions. Container orchestrators, they usually give you a set of Linux setups or Linux distributions that have been tested with. So I would by default stick to those because, again, there can be some side effects such as other file limit sizes and so on, which can be rather tricky to debug if you're running it on other systems. Similarly, if you have other services running on the same node, so imagine you're having a Cassandra, you're running on the same cluster as your container orchestrator, you should be careful in splitting up those resources properly, because the container orchestrator by default will think it has access to all the resources being available on that node. And if you're running other workloads next to it, this is actually not the case. So it might fail, or it might again get tricky to debug. Spreading out master nodes, or this could also be called spreading out your etcd, spreading out your Zookeeper quorum. So quorums, they're kind of the central point in your cluster which need to agree on certain decisions. So if those clusters or if those nodes are being spread out across high latency links, you'll end up with bad performance. So you should be careful in spreading out those vital nodes, such as the etcd quorum or the Zookeeper quorum in case of Mesos, across different regions. Agent attributes. So agent attributes, they allow you to specify, for example, where an agent is located. So if an agent is located in a certain rack, in a certain fault domain, you can specify that with attributes. You shouldn't change that once that has happened, because if you change the agent attributes and previous scheduling decisions have scheduled a task there exactly because it's on rack ABC in zone west, and you now change that, this will mess up scheduling decisions, because all of a sudden this task will run on a node where it shouldn't run. So try to set all attributes or all metadata for agents before you start them. Cluster upgrades. Cluster upgrades, they have gotten much easier over time. Still, it's kind of challenging. And the most important thing is to check the state before you upgrade. So often people start upgrading a failing cluster because they hope that a certain bug is fixed in the next version. And upgrading a failed cluster usually is a pretty bad idea. So you should first get your cluster in a healthy state and then upgrade. And again, back up before so you can restore your cluster if something goes wrong. I would skip over the upgrade procedure, but in short, what I personally really like about those container orchestrators is that the task, so the containers you're actually running on them, even though you're upgrading the system itself, they will keep on running. So you can do an upgrade without really affecting the users using your platform. Software upgrades. So software upgrades, especially automatic software upgrades, they're a really nice feature because you don't have to worry about your infrastructure. But again, we mentioned earlier that you want to have an infrastructure controlled by code. And if you have automated updates, this will all of a sudden change from what you have specified in your code because Docker is automatically upgrading. And Docker has a special track record of breaking things when you would upgrade from one Docker version to the other. So what could happen all of a sudden is that your containers are not running anymore because you now have switched to the next Docker version. It has gotten much better, but still I would have that in my infrastructure as code. And when I want to upgrade Docker, I do that via a code change, which I'm then deploying to my cluster, which then updates the Docker versions. So I want always explicit control of which versions are running anywhere. Day 2 operations. So again, these are all those shiny demos at presentations, at webcasts, or at a conference. So they always show you like really cool thing, how easy it is to set up something. In my experience, the hard thing is not necessarily setting up a demo or a cool use case, but the hard thing is to keep it running for production workloads. So you should consider day 2 operations, which is the actual challenging part of running anything in production. So day 2 operations, this includes configuration upgrades. I want to upgrade from one version to the next. I want to add more nodes to my Cassandra cluster or anything configuration related. Also, upgrades. I want to upgrade from Cassandra version 1 to Cassandra version 2, for example. Cluster maintenance, how can I back up my actual cluster? How can I upgrade my actual cluster? And as we've seen earlier, really important topics, monitoring. And also you should consider upfront how you can debug your system in a sustainable fashion. So for example, do you have to give SSH access to all nodes, to all your developers, or can you find a smarter way of doing that? Metrics, and drilling once more on monitoring. So metrics you should look out for are how utilized is your cluster? Are your resources being optimally used, or are you wasting resources right now? And also, how is the system performing over time? Is it picking up more and more resources? Are latencies getting worse, or is your cluster remaining in a happy, healthy state? Overall, there are 3 kind of resources you want to watch out for. And as mentioned earlier, this is on an application level, on a container level, and also on a system level itself. At the end, I actually have here a production checklist, but looking at the time, I would actually just leave that in the slides. So this is kind of helpful if you just want to browse through and see what you should be monitoring for, what metrics exactly. Maybe the one thing I would urge you to monitor for, still kind of relevant, is any Java-related app, which is critical, such as Zookeeper, for example. You should monitor for garbage collection times. So just to make sure that there are certain scenarios when garbage collection takes over. And so for any JVM-based application, especially the critical ones, this is something I personally would monitor rather vigorously. And yeah, this brings me to my last slide, and I hope to see many of you in Amsterdam for Codemotion World Amsterdam. So this is beginning of May, and I heard it's a great time to be in Amsterdam around there. And this gives us some time to ask questions, and I'll switch over to the question plane to see whether there are any so far. No? Then thank you very much for listening. Have a great evening and have a great rest of this week. Thank you for listening.